All right. So again, this lecture is about discrete continuous life cycle models. As mentioned by Mike, I realized that a lot of this materials is known to many of you, but we still go from the basics, you know, to get everybody on the same page. And actually, the simpler case is the real foundation of everything exciting that follows on. There we are. Let's first establish the discrete continuous choice. Their combinations are all around us. In pretty much every model can be set up in one way or another as a combination of discrete continuous choice. How much you work, when to retire, or when to buy a house, how much to save, when to buy durables, you know, what car to buy and how much to drive it. All a ton of applications of the combination of the choices. But we usually model them separately. We either convert everything to continuous choices, or we convert all the choices into the discrete choices. And that's because it's more convenient. If you try to work seriously with discrete continuous combination, what you usually find is that the model becomes non-concave, the first order conditions become non-sufficient, you get kinks in the value functions and discontinuities in the policy functions, as Mike previewed in the previous hour. So we can still work with this, with value function iteration, right? Just take it to a standard Bellman equation solver. But then we have to face the problem, you know, of needing the global optimizer when you search for that optimal combination of discrete and continuous choices in each point of your state space. And that's because the problem is non-concave. We need to track and hopefully keep track of the kinks, because they seem to matter in the numerical procedures that we normally use in solving these models. So you can't just run quadrature on the kinky function because it's not designed for it. So we need to, or we may, you know, think of developing special procedures for the non-smooth objects in general. So the plan for the lecture is I'm going to start with the original EGM, endogenous grid point method. And as I said, I realized that most of you probably know about it, but let's get everybody on the same page. And then I want to talk about the discrete continuous version of the EGM. And it will come in two flavors. The first flavor, we just take it as face value and not do anything with the problem. Let's just, you know, toughen up and solve it. And you will see that, you know, it is not easy. And then we go into this relaxation of the setting where we add a little bit of magic of extreme value distributed taste shocks, and things become much more tractable and easy to work with. And I want to say a few words on the most recent extensions with multiple dimensions of this, but you know, this is just going to be a few words, but I'm very happy to talk with those of you who are interested in this later on. All right, so what is EGM? A method of endogenous grid points. That's essentially a fast and really a miracle method for solving a very particular class of life cycle dynamic models. What's important to mention, it doesn't matter which horizons you have, can be both finite or infinite horizons. You usually want to have a concave monotone and differentiable utility function. Moreover, that's not on the slide. If the marginal utility is analytically invertible, that's when you get the most benefit, right? And in the standard setup, it's a one continuous state variable, one continuous choice variable. So think about consumption savings, wealth, and consumption. Now, what's also important is to have a particular structure on the law of motion of this continuous state variable, and we'll see how it works. And it's not that hard to formulate it in more general assumptions. It works well with borrowing constraints. A little bit more specific assumptions for the DCEGM. So now you want to have strictly concave monotone differentiable utility function for sure. Continuous state with a particular motion rule as before. Now we can add additional discrete states, and they can be discrete or discretized. But the important thing is that the law of motion has to be independent of M, which is the wealth at the beginning of the period, right? So there are already a restriction here on which models you can solve with this. You know, we stay here with one continuous and one discrete state choice variable, sorry. But of course, discrete choice variable can encode any number of discrete choices. All right. What's the learning outcome of today? If the model has one continuous choice and additional discrete choices, use DCEGM. That's basically a so much better way to solve these kinds of models. I think it applies to endogenous grid approach in general. If your model fits one of the, the original or one of the generalizations, it's just so much faster. You gain speed and accuracy in the same time. It doesn't happen very often. So it's definitely something to have in your toolbox. And even if you're working with the models that, don't feed any of these classes, this is a trick which is very useful to know, because maybe you can separate out one choice in your complicated model and apply this technique to it, right? And this way simplify your overall solution method. So the main point is that DCEGM avoids all root findings, which gives it speed, right? So you don't need to solve for any optimization problem or any equation as you go through. We have a question already.
So how does it work with normal shocks?
So the shocks is not even part of the picture here. The shocks you will have to treat in the usual way. So you can calculate expectations within this framework as you would do with value function iterations.
Can you just repeat the question going forward?
Oh yeah.
And then
oh yeah, that's right. Sorry. So the shock was, the question was, how do we deal with normal shocks in the model? And we deal, the answer is we deal it in a completely normal way. No change there. Okay, so I'm saying that if the utility is separable in continuous and discrete choices, then DCEGM is also very efficient in dealing with credit constraints, which is useful. Again, as I said, so we add extreme value taste shocks to make things smooth and easier to work with. Yeah, you should know it. Okay. So let's start with EGM. Very basic setup, and I'll try to go fast through this, but let's see how it goes. Let's look at the consumption savings model without income, right? So I want to have for this, potentially stochastic returns, but let's just stay with deterministic for simplicity. So think about cake eating problem. We had something in the beginning of the period that's MT. Now we consume C, which is limited, bounded above. And let's make a notation A, that is your end of period wealth, right? So that's what's left after consumption. Utility function, well, CRA. Now this has an analytical solution, which is nice. So, a second talk that Michael Keane usually gives in the school is talk about practical issues of structural estimation. And we link to the video in the teaching repository. This is in spirit of his idea and sort of drive to test the numerical solution against some case that we can solve analytically. Okay, so we're looking at this problem with an analytical solution, and that's nice, right? Because whatever we solve numerically, then we can just directly compare. Just to be on the same page, so this is the solution of the finite cycle model, right? We get a bunch of value functions. Each value function corresponds to a particular time period and a bunch of decision rules, right? Policy functions. Yeah, I usually ask, where's the solution for the infinite horizon model here? But I guess everybody sees the solution for the infinite horizon model in the picture, right? Think about it. So we can go from period to period and solve, every time period separately, get a new policy function. And you can think of this 45-degree line as the terminal period solution, because you consume all the wealth you have. You don't have any future. But then we may converge. And so somewhere here down below, the converged policy function would solve it for the infinite horizon specification. All right, so now let's just introduce income. Income is going to be this Y, potentially stochastic, and suddenly we don't have any analytical solution anymore. So what do we do then? Then we do value function iterations, right? Traditionally, we fix greed over wealth. We just look at every possible state this model can be in. We have some terminal solution or initial guess for the value function if it's an infinite horizon case. And then we iterate over time in a backwards induction manner, and we solve the Bellman equation. So the thing to note here is that, see, it starts with fixing the greed over states. Right, that's the first step in solving dynamic models with backwards induction. Oh, okay. I was going to run some code. I'm not sure if in this audience it's the right thing to do to run MATLAB, but let's do it. So you have both MATLAB and Python implementations in the repository, so I'm safe. But these slides are made with MATLAB. Right, so we have a few classes here implementing the Deaton-Phelps model and the retirement model that we'll come back to, and a nice helper class called Polyline, which implements the. Oh, we need to. Okay. Is this more visible? In principle, you can see you have all of this code in the repository as well. So anyway, I have this run file for this lecture. We're just going to create the model object here, right, by creating the instance of that class. A little bit of a clunky way to run MATLAB code without the MATLAB graphical interface. So what do I have to have here? Right, so we are observing now the solution by value function iteration. Iterations, each dot is a solution of a particular point in the state space. And you can see we're solving for 25 periods, backwards induction. This is finite horizons implementation. It takes some time, you know, and that's understandable because for each point of the state space, you have to find that optimal consumption, right? And that's an optimization problem. Oh, did it run? Oh, wait a second. Sorry, I'm not quite prepared. All right, so that was the value function iteration implementation of the of this model, right? I just wanted to show you the code and we can compare. Now let's remember what the Euler equation is. Very simple, right? We write the first order conditions for the Bellman equation over here, and then we differentiate the value function itself using the envelope condition. We notice that you know, this object here is the same as this with a different sign, and that's due to our intertemporal budget constraint, really. And then we can plug in the the marginal value function with respect to the amount of wealth. That's the same as the marginal utility function evaluated at the optimal consumption level. Shift this forward and plug it back in, you get the Euler equation that I'm sure everybody is very familiar with. And that's, of course, another way to approach the problem. We can organize the iterations, which are, well, I'm saying solving Euler equation time iterations. I think that's also referred to in the literature. Again, you know, fix the grid over the state space, go backwards in time, start with some terminal case, and in each point of the grid of the state space, in each time period, solve the Euler equation, right? And find the optimal consumption corresponding to that point on the grid. Well, again, the thing to see is that we fix the grid over the states as a first step. And again, you know, we're not solving the optimization problem. We're solving a first order condition, the equation instead. But computationally, that's the same thing, right? So computationally, that's as hard as finding the optimal level of consumption in the previous solution method, the VFI. All right, so here's the dream. What if root finding, no root finding is necessary? Well, we don't have all of these complications, but the one that I want to point out is that, you know, if you have credit constraints, that means that there is a level of wealth at which the credit constraint just starts to bind, okay? Because if you have less wealth than you consume everything, you have a little bit more than you start saving. So that particular point is going to be very hard to pinpoint with the fixed grid over wealth, right? Because we don't know where it is, but we just assume a grid on wealth when we solve the problem. What that means is that there's this little spot is going to be smoothed out, and you can't really make the grid dense enough to find that unless you do some specific procedure to find that exact point. But what that entails to is that your solution is not completely accurate for this model with credit constraints. And that can lead to errors in simulations and errors in the estimates. Okay, so endogenous grid point method, due to Carroll 2006, the main idea of the method is that we're turning this solver around. So instead of searching for the optimal decision in each point of the state space, as we did with all previous methods, we look for the state variable, the level of the wealth, okay, where some chosen decision that we sort of come up with, right, turns out to be optimal. Okay, and that's really in the heart of the endogenous grid point methods everywhere. So instead of going through the grid on states, you go through the grid of potential decisions, and for each of those decisions, you find the point in the state space where it would be optimal according to our conditions. Okay, and now it turns out that where it would be optimal is easy to compute. It's a direct computation in a certain class of problems. So here how it goes. It is still backwards induction, right? So we start with terminal period where you consume everything, or we start with some arbitrary guess of the policy function. And then we iterate by taking the next value A, and the next, what I mean by the next is, you know, the next on some fixed grid, for example. Given this end of period savings, we can calculate the next period wealth according to the intertemporal budget, right? So in our case, it's just basically grows with a return, this A. And remember, A is just what's left after consumption in period C. That's what we start with. So post-decision states, these are also called. Since we already have the policy function for the next period, and that's because we're doing the backwards induction, so we always have the next period solution at hand, we can calculate the optimal consumption in the next period, given that wealth, right? And then the key step, if the marginal utility function is invertible, then we just invert the early equation. We already have this, right? We can calculate the right-hand side of the early equation. And if we can invert the marginal utility analytically, then we just calculate the optimal level of consumption today in this current period. Well, what's left to do is just add that, the optimal level of consumption, to where we started, to how much wealth we would end up that period with. And this gives us the wealth where this consumption and this savings is optimal according to the early equation. Okay? And then we continue. Then we continue going to the next point on this fixed grid of savings. And essentially, we're building this correspondence by going through the grid on savings. We build the correspondence between the calculated wealth and the calculated optimal consumption. And that, of course, gives us the approximation of the policy function in the current period. Once that is done, we can go to the previous time period. As you can see, there is no root finding. This is all just direct computation. And so it takes no time. The other way to think about this is to think of the solution of the policy function that we calculate as a parameterized curve where A is a parameter, and here's your C and M, right? We need to find the function C of M, which is the policy function, you know, dictating us what's the optimal way to consume given wealth M. And just sort of rewriting the early equation and going through the same set of steps that were on the previous slide, we can see that we basically just change this A, the parameter, and we get the pairs C and M, which is the solution. Of course, we need to have some policy function C naught here, which is basically the next period policy function, or the previous iteration policy function if we're doing infinite horizons and we converge in policy function space. All right, so that's EGM. It's very simple, as you can see. And that's why, you know, if you can do it, do it. If the model is allowing for that. Here's the implementation in MATLAB in 11 lines, but the actual EGM loop is right here. And you can see it calls some functions. It calls quadrature points, calculator, and something else. But essentially, this is the solution for a full-blown consumption savings model for the whole life cycle. And it works very, very fast. I don't remember the parameters of this comparison, but you can see the earlier solver that we just talked about takes, you know, times and times more runtime than EGM, while the accuracy measured as the maximum absolute error in the policy function is much better with EGM. Point being is that with this method, we gain both speed and accuracy. All right, let's go back to my comparison here. So now we don't want to run VFI, we want to run EGM. Right, and it's done. And it's not done once, it's done 100 times. And with an average running speed of 6 thousandths of a second. And that's the same problem, right? Okay. Now, the exercise here is simulate flat consumption paths. And again, I can refer to the talk on practical aspects of structural estimation by Mike King, which is on YouTube and which you definitely should watch. Very nice watch for sort of life around what we do. And there he talks about this making it flat, right? You know, if we have the situation where the early equation cancels out on both sides. So let's look at the early equation again here. So imagine that we don't have any randomness. So E disappears, the expectation we don't need. This is 1, or rather R times beta is 1. Then we have just the equality of the marginal utility functions, and that means that we have to have a flat consumption profile, right? The test is, let's try to solve the model under those conditions and simulate the consumption profile and see, is it flat or not? And because of the inaccuracies of the numerical solution, you know, once we don't get the flat consumption profile, that means that the solution method has some inbuilt errors. And that's a nice test. And so this is, we're doing it here, I believe. So we can easily simulate some consumption paths. That's a very sort of straightforward algorithm. I'm just simulating from uniform distribution of the initial wealth and then applying. I'm applying the policy functions here. But here's the setup where we say that the discount factor has to correspond to the rate of return. I have to speak in the microphone, sorry. In the right way. And sigma equals 0 means that we have a deterministic problem. Okay. Let's try it with EGM first. And here's 2 consumption profiles. Well, making a picture of 2 is, you could say it's a little bit of a cheat. But see, MATLAB has this tendency of adjusting the limits on the Y. And of course, if you just simulate 1 consumption profile, it could jiggle a little bit with numerical precision, essentially, or with the precision of the solver that we're using. But here, the difference between this initial wealth, this is 688. It's not readable, I realize. So this is about 7, and this is about 6.73. So they're pretty close. Okay, this is EGM, and let's look what VFI produces. And of course, you can tweak the VFI. We have to wait for a little bit because we're using VFI. That's part of life. So the same conditions, essentially, I think I'm even fixing the random seed. So we will start from the same levels of wealth initially, and you can see what we get in the VFI solver. And again, you can, of course, tweak the grids and you can solve it more accurately. And the time will increase, obviously, but also think about that little kink on the policy function where you switch from being credit constrained to being not credit constrained. So that one point is very hard to get. I would say pretty impossible to get with the VFI unless you're doing something very specific. And that becomes very important if your simulation, you know, starts or passes sometime around that point where the accuracy is lost. All right. So let's talk a little bit more in detail about exactly that. So we can show that if the utility function is monotonic concave, then the end of period assets A is a non-decreasing function of M. And that's very useful. That means that if we run the EGM loop with savings equals 0, so the situation where you've consumed everything and you left nothing for tomorrow, right? But we actually do the EGM loop, so we're using the early equation to recover that point of wealth where that would be optimal. Right? Of course, you know, because the early equation only applies to internal solutions, I should have said that. That actually gives us that point where the credit constraint coincides with the early solution, with the interior solution. And that defines this point of wealth to the left of which you know your credit constraint. You know that because of this monotonicity of the savings function, you know, if you find that one point where you know, which corresponds to zero savings, the EGM will then produce other points. And we're looking here at the optimal consumption profile. So we have wealth on axis, and on Y, we have the optimal consumption. So this is C of M. And EGM produces you know, points one by one as we go through the grid on savings. The first point is corresponding to the to zero savings, to saving nothing. And because of that monotonicity, we know that to the left of it, we're credit constraint, which means that we consume everything, right? So we're just a 45-degree line, and we just need to add one point, essentially, do linear interpolation, and that gives us a very precise solution to the credit constraint region in this consumption savings problem. And this is the point that I was referring to, right? This point is really hard to get with VFI, with any sort of fixed grid on wealth. Once you fix the grid on wealth, then maybe you're missing this, and instead of this function, you may be working with something that goes like this, right? And if your simulation goes in this area somewhere, you inevitably, you will not get the flat profile in the simulated consumption. Okay, that basically says this. There's a question of how to evaluate the value function if you're solving the model with EGM. And that's not trivial because we will use it just in a second. Well, if you know the optimal policy function, that's a pretty direct calculation. But what happens here? Right, because you approximate, you calculate the solution in these points. But what happens in the credit constraint region? Well, it turns out that the solution is pretty simple. Because you can calculate the expected value of saving nothing, right? That's one of the points on the EGM loop. And then this value function is just the utility shifted up by this expected value of not saving anything, right? So in fact, in this region here, we have value function with basically analytical form. It's just the utility shifted up. Wonderful. All right. Do we have questions so far? That's a good point to take a little break. Questions for EGM? Are you convinced that this is the method to use if you're solving consumption savings models? Yay, okay. All right, let's add discrete choice. So this is based on the paper with John and Bertel and Thomas Jorgensen, as I said. And we're looking at both of these cases where we do and we don't have the smoothing extreme value shocks. And the paper that we sort of started, well, we coincided with I'd have to say, you know, the reason that we went on, isn't that right, Bertel? And continued with the second case was because Julia Falla published a paper which was very similar, although not the same, and about the same time. All right, so we need a different model now. We need a model with discrete choice. And the simplest example that we can think of is this retirement model with absorbing retirement. So you have consumption savings in both of these branches, but in one case here corresponds to retiring, okay? One case corresponds to continuing to work. And so the bottom case here is the the decision to remain worker. You can see that there's a second state variable in the Bellman equation, which basically says whether I'm a worker or I'm already retired. right? So the first choice on the top is to consume optimally and also retire. And so in the next period, you become retired. The second choice, the second option, discrete option, is to consume optimally, but continue working. And then you get the wage. And in here also, I assume that the wage is paid in the next period, but that's a technical assumption. Now, an important thing is that if you decide to retire, so if you're already a retiree, then you're basically back to the consumption savings model. You don't have a choice anymore, the discrete choice. You don't have a discrete choice anymore. This is just for pure illustration, right? It doesn't have to be like that. It's just so that we only talk about workers when we discuss these discontinuities and kinks. Similar utility function. Now, it turns out that this also has an analytical solution. And the solution is basically a bunch of cases where the optimal consumption is given on a specified interval over here, and all of these limits of the intervals are given with equations, if I remember correctly. You know, it takes a guy over there in the back of the room to write down something like that. But we can plot it, right? We can plot it, and you can see that all of these are the policy functions. This is the optimal level of consumption, okay? The optimal level of consumption given your cash in hand, given your wealth in the beginning of the period. All of the solutions have this 45-degree segment, and then a bunch of connected segments, and then a bunch of disconnected segments. And that's your optimal consumption in the model where you have continuous and discrete choice. Now, you would see that, you know, there's a lot of discontinuities in this policy functions, and this is only due to adding this one absorbing retirement choice, which is probably the easiest way we could introduce a discrete choice in the consumption savings model. And that's the immediate consequences. You get to this very complicated case right away. So let's see why. And the road is this. So let's try to avoid root finding. Right? So let's try to preserve the main quality of EGM, that it's fast. And well, it would be nice to be efficient with credit constraints as we were before. So the idea is to run EGM step for every discrete choice. All right? And if we have an optimal consumption for, you know, conditional and discrete choice, we can compute the value functions the way I showed before. This will now be discrete choice specific values. And then we can compare them, right? We can just compare the value functions corresponding to different discrete options. These functions will be basically drawn as a functions of wealth through the EGM step. But we still can compare them, and we can find the optimal switching point. So the point where they intersect, where you switch from, you know, being retired to continue, or continuing the worker or being retired. And then we can reconstruct the overall consumption rule from that by just combining the rules from the left and the right of the kink. So we have the value function corresponding to the discrete choice of working. We have a value function corresponding to the discrete choice of retiring. Each of that value function is a solution essentially, right? So it comes with its own consumption, optimal consumption rule. But then we can combine them together, right? And see, we're not doing the root finding. We can actually still have efficient treatment of credit constraint. But what we now have to do, we have to evaluate value functions, not just the policy functions compared to before. And we need to calculate this upper envelope. We need to calculate the maximum of the collection, potentially a collection of value functions for all possible values of wealth. The question here is whether early equation is still a valid condition for optimality. The answer is yes, due to this paper. And let's just proceed, okay? Terminal period, that's when we don't have any future. The value functions here are corresponding to retirement and work. And remember, we set the problem such that you get wage in the next time period. So in the last period, it makes no sense to work because you will only get the wage next period, which doesn't exist. And so we clearly have the retirement value to be higher than the working value for all possible values of wealth. But if we go back, now we start seeing these intersections. And by the way, I have to say that this green line, it continues analytically down here as we have looked at before. But so this graph just doesn't show that analytical part in the created constraint region. But we get the intersection point. Yep.
Is that innocuous? The setting that you get the earnings next period? That seems sort of unusual.
That's okay. So the question is, what's the implications of setting that the wage is paid in the next period? We would have this picture in the very last period if we had wage in the same period. So yeah, it doesn't matter here. If the wage is stochastic and the shock is IID, then it's your choice whether you want to include the value of that shock into your state space and condition the labor supply decision on the shock, or you want to assume that labor supply decision is made before you know the shock, and then the shock can be integrated over together with all the rest of the risk in the model in the Bellman equation evaluation, right? So you basically don't have to include it into the state space. So that's really the trade-off. If you have IID wage shocks, then you may want to include it into the state space and condition choices, or you may not include it into the state space and then assume that the labor supply decision is made before the realization. And that's easier to compute, so I guess. Anyway, so we could have the other situation. We would just start with this picture, which would be a little bit harder to explain. Okay, so we have that intersection. What does it mean? The blue one is retirement, if I remember correctly. Blue one is retirement. So in the capital T minus 1, if you have more than this much wealth, then you retire. Then it's optimal to retire. If you're very poor, then it's still optimal to work, even in the last period or next to last period. Okay, that's what it means, right? The value functions. Zooming in, we calculate the upper envelope, that red line. And now the upper envelope becomes the maximum over both the continuous choice consumption and the discrete choice. So in the Bellman equation, the result of the maximization operator is the red line. That becomes our new value function. You immediately see it's not concave, right? So we have this kink in the value function just because we have compared two value functions together. And that's what we call the primary kink, and this is going to be a prominent feature, and I don't see how you can avoid it unless you do this additional assumptions that smooth this kink out. And this is the optimal consumption. Now the graph here, this vertical line doesn't exist, so don't pay attention to that. Why we have this drop in the optimal consumption? Well, because we're combining two different consumption rules together, right? On the left here, we had the consumption rule for the worker, and on the right, it's a consumption rule for the retiree. And when you combine them together, you get this this discontinuity. It's also very natural. Now, it's important not to interpret this as any sort of trajectory, right? So we shouldn't say, as your or I don't know, maybe we should be careful when we say as your wealth increases, then you sort of discontinuously change your consumption. That's not the case, because this is just the optimal rule, right? It says if your wealth is here, then it's optimal to consume this. If your wealth is here, then it's optimal to consume that. And we're still in the finite horizon problem. And your next period consumption can be completely different. There will be a different curve or different discontinuous function. So you never really move along here in time. You sort of find yourself at different points. Yep. At that kink point. So yeah, let's think about that. So if you're exactly here, so you're indifferent between the discrete choices. And yeah, I don't really know what you would do in the code. You have to somehow come up with a rule to settle this discrepancy and treat this as either or case. Maybe randomize it. So to sum up, what we've seen is that the discrete choice specific value functions intersect, and that's because of the trade-off between income and disutility of work, and the upper envelope creates the kink in the value function. Now here's the story of our life with, you know, we've then thought, okay, we got it, right? We got it. We just do the upper envelope and we continue doing that with the backwards induction. We have the solution. But like on the capital T minus 2, Bertel and me just got this picture. And it's kind of hard to see this guy here because, you know, it depends on the scale of the graph and you know, what's going on there. And then you zoom in and you see this kind of a butterfly picture. So what's going on there? You zoom in even more, and then we realized that we had this very strange zigzags in what should have been just a value function, right? That was very unclear. Then we realized that we sorted the endogenous grid. You know, wealth is here all the time and it's endogenous, right, as in the EGM step. So we actually sorted the grid and we got this very strange up and down. But what actually happened is that, you know, once we have a kink in the value function in the next period, when you solve the early equation, the derivative of the value function has a discontinuity, right? So as you sort of solve the early equation, it's not a concave problem anymore. So you have this additional solution that the early equation kind of nicely tracks, and the EGM step allows you to build all of the points that are not necessarily optimal. So then we just looked at the early equation, and again the vertical lines here, they don't exist. This is just a discontinuous. This is the residual of the early equation drawn for different levels of cash, of wealth. And it becomes obvious that for some levels of wealth, the early equation has two solutions. And that's the problem. So that's exactly what we saw here. You know, for this range of wealth, we would recover both solutions of the early equation. And, you know, using the early equation before was sufficient to find the optimal choices. Now it's insufficient. Why? Well, because the problem is not concave anymore. As simple as that. Just because we have a kink in the value function in the next period, we cannot rely on the early equation having one solution. All right. For some levels of wealth on the endogenous grid, the early equation has two solutions in this case. So what you actually have is this. You go through the grid of savings and you generate these points sort of one by one. And then at some stage, you know, at some next point on the grid over A, you see that the resulting wealth and resulting consumption sort of jumps back. Or resulting wealth is the more important aspect. I guess on the Y we have value in here. And what's the solution? Well, the solution, this is the value function again. So the solution is just to take the upper envelope, right? We're just comparing value. How do we find what's optimal to do? Just go back to the Bellman equation and maximize the maximums in the Bellman equation. And that's what we have drawn here. Right, so in order to filter out this suboptimal points recovered from the solving of the early equation, we can just simply take the upper envelope of this strange value function with this strange region.
Just maybe repeat the economic equation of the bilateral tax. So what I've worked, that's the point where I go working next period.
Okay.
Before, so I need that.
Let me find a picture here. So what we essentially have is this is the value function of retirement. Okay, here's the primary kink. It's optimal for you to be retired on the right side of it. And so here the resulting value function, right? The value function in the Bellman equation coincides with the retirement choice specific value. On this side, it's optimal to be working, right? But there's the secondary kink here, which is due to the fact that there is a primary kink in the next period. Does it make sense? So in the capital T, we don't have this. We only have one kink. In the capital T minus 2, because we have this kink in the capital T, we have a discontinuity in the early equation and two solutions. And we basically here, we jump from one solution to the other. What's the economic interpretation? This is the exact point where you know you would be exactly at the kink in the next time period. That's what it is. Okay. Well, so this is once again sort of with numbers, we can show that we can actually track the situation, right? Under certain conditions on the utility function, we can show that the monotonicity of the savings actually holds. So if we can generate the points on the grid of savings going from the lowest savings to the higher, we should not see wealth, resulting wealth going back. And so every time that happens, you can algorithmically sort of cut this resulting stream of points in half and calculate the upper envelope on these as separate segments. And that's the idea of correction, of the secondary envelope correction of what comes out of EGM, essentially. And you know, with consumption, we do exactly the same. So we observe the discontinuous jump in consumption corresponding to the next period primary kink in the value function. And because we know how to filter out the suboptimal points, the points where the early equation is solved, but which don't correspond to the optimal choice, then we know how to filter out the suboptimal points in the consumption function as well. You know, bring it all together, your consumption function starts collecting the discontinuity points. So in capital T minus 2, you have a discontinuity point here, which corresponds to the primary kink. That's the switch between working and consumption, and has another discontinuity over here, which corresponds to the next period kink in the value function and the next period discontinuity in the consumption function. This is capital T minus 2. You see where it's going, right? This is your collection of optimal consumption functions as you go through the backwards induction. So these kinks just keep accumulating. In capital T, you have 45-degree line. Here you have only one primary kink. In the capital T minus 2, you have two kinks and so forth. And that explains that crazy picture of the optimal savings, optimal consumption function in the analytical solution. So that's exactly what's going on. And yeah, you can see that the optimal point of retirement also declines as you go through time. Now, these are time periods. In the last time period, you just want to be retired, and you retire with more and more wealth optimally as you go back, right? This is very natural. If you're a young person, you have to have more wealth to retire at that time. All right. So what do we have? We have to add an additional step in this DCEGM algorithm, right? We now have to filter out this spurious solutions by doing the secondary upper envelope on the choice-specific value functions that come out of the EGM step. All right. It's important to realize that this is not because of the solution method that we're applying to the problem, right? All these kinks and discontinuities, the way I've explained them, they kind of seem to be coming out of the solver. You know, if you just do VFI, then we don't have all this problem. No, you do. You just don't see them, right? So these problems, and these are the properties of the mathematical formulation of this model. And we may choose not to sort of focus on these and pretend that they are not there or they're not important. But actually, in every problem with combination of discrete continuous choice, you have this. It's still possible to do VFI. And I would say that the approach where you discretize both continuous and discrete choice, so you discretize the continuous choice and basically solve the problem on the grid, is not a bad approach. It's not accurate because you lose due to discretization, but at least you get the global solution in each point of the state space, right? So that's a justification for doing simple discretization solvers in this setting when you have continuous and discrete combination in the same model. All right, and it also says here that DCEGM matches the analytical solution perfectly, which is, you know, that same test that we're doing on this problem, since we'll also have the analytical solution in the very beginning. All right, here's the interesting question, right? Now, let's run the same the same test for the situation where beta r equals 1, but in the problem that we just looked at. And you can think what you expect to see in the simulated consumption path. Right, so here I'm setting up the model. Here I'm setting up the model for retirement savings without the shocks, right? Without any stochasticity. It's completely deterministic model, and I have this correspondence between beta and return, so that we have the case where we expect flat consumption profiles. And let me run this. It takes a little bit more time because we have to do more work, right? So I would say it's about 10 times slower than the original EGM. Of course, it, I mean, depends on how many choices and how complicated the model is otherwise. But here's the end result, right? I don't know if you can see these dashed lines. These are the points where the simulated agent retired. Okay, we've simulated the agent starting with this and this initial wealth. This is time on the horizon. I don't know if you can see this plots, but hopefully somebody can run this code on your own computers as well. And you see that simulated consumption profiles are still flat, even though they retire in the middle of it. So, and that's no surprise, actually. That's what we should expect, because these people are hyper rational, right? They know everything that's ahead of them. They can solve the problem completely, and we made them like constant consumption. So they solved the model with consumption savings and retirement in the same setting in such a way that to flatten their consumption profile, even through the change of their state. But this is mind-blowing on the other hand, because you know, this is not very well seen, but you know, going back to the nice analytical solution picture there. So this is what our hyper-rational person calculated, okay? And then they started somewhere, you know, we're in the initial wealth, and they've consumed the corresponding amount. And they've, in the simulation, right, they've been left with some new value of wealth in the next period, and they looked at the completely different function. This is finite horizon, so different functions. In the next period, also very discontinuous, and they got this, and they got exactly the same consumption, right, in the next period. So even though the policy functions look crazy like that, our you know, hyper rational individual is able to jump between these little steps and around the discontinuities in a perfect way, such that the simulated consumption path is completely flat. That's fascinating, right? And so this is to emphasize the difference between the solution of the model and the simulated consumption path, right? Even though the solution is you know, has kinks and discontinuities, doesn't mean that they translate directly in the simulated consumption path, which is data. We don't have to see these jumps in the data. Yes, the solution is complicated, but the data is, you know, corresponds to the simulated consumption path, which don't have to have kinks. How much time do I have? About half an hour? Okay, so what happens when you have randomness in the model? Well, things become easier on one hand, because say random shocks, random returns, they start smoothing out the secondary kink. What's the logic with that? Well, you don't know exactly when, you know, in period T, you would be at the kink at period T+1. Right, so that's very logical. But the primary kinks, they remain. Because even if you have random returns, you know, this comparing of the values does not go anywhere. So the additional random components of the model, they smooth out the secondary kinks, yet, but they cannot smooth the primary kink. And that's actually brings additional problems. So if we have random returns, then we have to calculate expectations in the model, right? But now we calculate expectations of the functions which have kinks or discontinuities even. And that means that we have to have some, you know, special approach to calculate those expectations correctly. You can't just use quadrature anymore. And in fact, if you do, you will get very strange, spurious additional discontinuities in kinks just because you don't really know where the quadrature points land on those discontinuous functions that you calculate the expectation of. Right, so this brings an additional complication for the numerical methods. Of course, the right thing would be to track where the discontinuities are and sort of calculate the expectation by part and do some, a separate quadrature on, say, on intervals or something. We have a question.
Secondary and primary things. So primary things are the discontinuities in the value function, and secondary things in the policy function.
So
for the interpretations to do the kind right. Primary things are the ones in the last paper, and secondary things are the more.
Okay, so let me repeat. The question is the distinction between the primary and secondary kinks. And let me go back to that picture that Mike also showed. The primary kink, what we call the primary kink, is the kink that is there because you have to compare the discrete options in any time period. So if you have to compare discrete options where you compare the choice specific value functions, that gives you the primary kink. Okay, the secondary kink is kind of an echo of the primary kink in the next time period. So this is something that you observe in the deterministic model due to the fact that you have kinks tomorrow. Kink in the value function and discontinuity in the consumption function, in the policy function. So they always come together, right? A kink in the value function corresponds to the discontinuity in the consumption function. And that applies to both primary and secondary. Okay, but the secondary is kind of a technical difficulty because we're solving a non-convex problem. Another question.
How these random recur are going to this model? I mean, what's this R in reality? Is that the same as the income shock, or we need to another taser shock?
So the question is about the nature of the random returns. So I'm using random returns here, and we can look at what happens to the solution. This is what happens to the solution, right? The vertical lines again are discontinuities, but the second kink here, and this is capital T minus 3. The second one happens to be smoothed out. Now I'm talking about the random returns as an example of some random elements in the model. Okay, so this can be a random, this can be shocks to the earnings. So this can be random returns. So this can be a combination of the two, or whatever other, random components in the model you will have will help you smooth out the secondary kink. With the logic again, that it's impossible to predict precisely what level of wealth today will bring you to the kink point tomorrow. Okay, so we ran a few simulations here, and you can see that as you go back in time with a certain level of randomness in the returns, then it also seems that over time this kinks start smoothing out. And I believe this is made with the quadrature with very many points to minimize the effect of the fact that we are calculating the expectation of the non-smooth function. But the point also is that, with sigma equals 0.2 here, we still have the discontinuity, which you don't really see because of this sloppy plot, but there's a vertical section here. There's a discontinuity there. It sort of starts being smooth, but not quite. And then you go to 0.22 and it's smooth completely. The takeaway point is that it's very hard up front to know how much randomness in the model smoothes your problem completely. And that means, right, that even with random with stochastic models, we have to have this secondary envelope correction because we don't know whether there's enough randomness in the model not to have the secondary kinks. Okay, let's now go to the extreme value shocks. It would be nice to smooth all of the kinks. Okay, and from the point of view of computation, so that we're working with smooth objects, but also, because we have discrete choice in this model, shouldn't we apply everything that we know about modeling discrete choices, right? And have some sort of continuation to yesterday, So let's try extreme value shocks. They're introduced in the same way as in the discrete choice problem, right? So we will write the Bellman equations just in a second, but we add an RID extreme value shock to each of the discrete alternative. Of course, we're choosing them for computational just to be able to have analytical expectations, but you don't have to do it. You would just have to calculate more complicated expectations. So this is an illustration. Now, an important point is that you can actually interpret them as structural, and here by structural I mean that the econometrician does not observe certain states in this model and treats the data, the choice data, as something that comes from the decision maker who knows the shocks, right? But I don't know. And therefore, I get choice probabilities instead of exactly predicted choices. Or you can also think of this as just simple logit smoothing of this problem. And then you would not estimate the degree of the smoothing. You would probably just fix it as a tuning in parameter. And now another point is that they actually work well with the other shocks that you may have in the model. The reason being is that this additional discrete choice shocks, they smooth out the primary kink. You know, the idea is that if we add some randomness in how you choose when to retire or at what wealth to retire, on what wealth it's optimal to retire, then you avoid this comparison of the value functions. Instead of comparing, you now have a logically sort of a logit smooth function there, and you have choice probabilities. Right? Does it make sense? So, and that's therefore the way to smooth out the primary kink. But in addition, you know, randomness, random returns, or whatever, random labor shocks, they can take care of the secondary kinks as well. But again, no, complete smoothing is not guaranteed. It all depends on parameters. This is the short that I was given in Denmark, that extreme value is the new normal. But let's look at the Bellman equations. So now we want to rewrite the same retirement problem with absorbing retirement in the choice specific value function space. So instead of writing that, I mean, I can write the Bellman equation, right? We add this EV shocks to each of the alternatives, but now we want to focus on the choice specific values. And now they have three arguments, right? This is your wealth in the beginning of the period, your state. The second argument is the state, whether you're a worker or you're a retiree here. And the third argument corresponds to the choice that you are making in that state. And we have this deterministic parts of the value for choice specific value functions written up like this. So not much has changed, except now that we have two functions to work with instead of one. And we're making the max here. But then, of course, when we calculate the expectation of that function, we get the log sum as a smooth max function that plugs into the Bellman equation. And again, just for the illustration purposes, I'm keeping this the same. It doesn't have to be absorbing. You may have a similar structure on the retirement if you want to allow going back to work. Nothing really changes. It's just for illustration. Or rather than nothing really changes, you do the same thing for the retirees as you do for workers. Okay, so it's worth looking at what happens to the early equation. So the logic here is this. Before, when we had sort of the hard switch between being a worker and being a retiree in the next time period, you're either on one side of the kink or you're on the other side of the kink. So we had this, you know, something going on there. You had to know we had two kind of early equations for two different sides of the solution. Now, if we just do the derivation of the early equation, we nicely get choice probabilities of the next time period. And this is due to the fact that differentiating the log sum function, you get a choice probability. So you are essentially smoothing this, or taking the average of the marginal utility in the next period with choice probabilities. And that smoothes out the early equation, right? The choice probability are, of course, standard. It smoothes out the early equation. And now if we draw the early residual, you know, the case with no taste shocks, that was a discontinuous curve here, discontinuous function with two solutions. That's drawn for a particular level of wealth. And for that particular level of wealth, we want to find the optimal consumption. To do that, we solve the early equation. Well, not solve, we invert it, right, in the EGM step. But the early equation crosses 0 at 2 points here in the no taste shock case. But if we add taste shocks, it becomes smooth, you know, but now it has 3 solutions. Right, so is it easy or not? Well, I don't have a picture for that. Well, we have the machinery of secondary envelope, right? So we don't really know how much smoothing we add here. We may add enough smoothing to go like this, right? We may completely smooth out the problem with discrete choice shocks, with the extreme value shocks, or maybe not. So again, this is the question of the quantity, but the takeaway is that we still have to have the secondary envelope correction in the algorithm to take care of those cases where we may still have discontinuities. But on the other hand, we don't have to do any comparison of the choice-specific value functions anymore. And we don't need to reconstruct the consumption function because we are working in a completely different space, right? We're working in the choice-specific value function space, and we solve the model by solving 4 discrete choice specific value functions and construct choice probabilities by plugging them into the logit formula. So on one hand, the solver becomes simpler. On the other hand, you have to kind of keep track of more objects. And the main point is that the primary upper envelope, the calculation around the primary kink, is now completely replaced by calculating the choice probabilities. Okay, in the logs. Now we have a theorem in the paper which shows that if you treat these EV random components in the utility as a logit smoother, then you can approximate the solution of the non-smooth function, of the non-smooth problem with any degree of accuracy by changing the sigma. So there's an upper bound. D is the number of choices. This is your betas. They are less than 1, so they converge even in the infinite horizon sense case, right? So by changing sigma, you can limit the error that you introduce by the discrete choices or extreme value choices attached to the discrete alternatives. If you want to interpret them as a logit smoother, as a technical thing, right? If they're not structural, you don't want to interpret them as something that you don't observe, then you can say, okay, I'm adding this to be able to solve the problem, and here's the maximum error that I'm making on my solution. Okay, I guess we can skip this. Let's talk a little bit about the credit constraints. Remember this, it's the same logic applies essentially. We have to have an additional assumption of separability of the, okay, let me go through this slowly. Before we connected the dots, right? We connected the dots between 0 and this point that we recovered by doing the EGM step with 0 savings. If you have nothing in the end of the period, then you know, by inverting the early equation, you get that exact level of wealth where the credit constraint is not binding anymore. Okay, that corresponds to A being 0. We have to have, if we have the additive separability in consumption and discrete choice in the utility function, then the situation that we're in is this. We can calculate this MCC, the boundary of the credit constraint region. We can calculate it for each discrete choice, right? We know that the value functions have analytical solution to the left of it. And the analytical solution looks like this. We can calculate the expected value of saving 0 corresponding to the each discrete choice. And then if there's this separability, so that utility of consumption is, you know, is additively separate to the utility of the discrete things in the model, then we still have that analytical form of the utility function, I'm sorry, of the value function in the constraint region, where the utility is just shifted by a constant. All right. And in this case, well, first of all, we know that that means that in this credit constraint region, the value functions don't intersect, right? They're just the utility of consuming everything shifted with different constants. So if we're solving the deterministic problem without the taste shocks, then we don't have to do anything in that region because we know value functions do not intersect there in this case. If we're doing the version with extreme value shocks, that means that, you know, the distance between the value functions, the discrete choice specific now value functions in that region is going to be constant, right? So the choice probabilities don't change. Bottom line, it is possible under this assumption to have the situation where you don't have to compute anything close to zero wealth. And that seems to be important because, you know, everything goes to, our usual utility functions go to minus infinity, close to zero, and you have to impose some sort of little tolerance there, right? But here in this case, we have everything in an analytical form. Wonderful. And so that's the picture which basically illustrates that. We have different cutoff values of wealth for different discrete choices, but we know that in this area here, you know, below the minimum of those cutoffs, everything can be just parallel. All right, questions to the DCEGM? Anything on the chat? No. No? Okay. Yeah, oh, sorry.
It's a bit of a technical question. You talked about keeping track of the discontinuity points.
Right.
How would you find you have to interpolate the value factor functions to get them? What can you set your grid such that you find points?
So think about the picture where we had the value functions crossing, right? You can calculate that point more or less accurate by interpolating both of these functions in your preferred way and calculating the intersection point and kind of remembering that intersection point that, you know, in that particular time period, the value function has a kink there. The choice, the consumption policy function has a discontinuity there. When you go back, remembering where that kink was, if you need to calculate an integral, some sort of expectation, right? Then you can break your calculation to the left of that point, to the right of that point, and take appropriate care of that kink in the numerical procedure, right? In the capital T minus 2, you will have 2 of those to keep track of. And in principle, you can again calculate them in the algorithmic way and then adjust the numerical procedure to take into account where those kinks are in the next period. But because the kinks accumulate, you know, it just becomes tedious. Oh, I didn't repeat the question. But yes, yeah. To find the exact point where the 2 value functions intersect. So the question about how to keep track of the kinks, right? That's the discussion. To find the exact to certain tolerance, of course. But yes, you interpolate both of the value functions and find the intersections of the interpolated functions, for example. I mean, that's very, very easy with linear interpolations, right? That's just a linear equation.
Now there's a question on the chat room.
Yep.
It's regarding where you put the measurement error in the model. And so right now, the question is, can you also add it to the marginal utility of consumption directly?
So I haven't said anything about estimating these models yet, right? So I guess this would be a question of how you use the solution of these models to estimate it on the data. I'm not completely sure. So in order to have a measurement error appear in the marginal utility, you would have to introduce it in the structure of the model in a particular way, right? So probably you would have to make an assumption on the functional form of the utility function. I think that would be the answer to the question. But, you know, an approach that it has been taken before is that to assume that the data contains measurement errors, right? And then form the likelihood by taking the solution of the model and assuming there is some measurement error around that solution and form the likelihood from that. Yeah. All right, so let's talk about multi-dimensional generalizations of these methods. They are hard. They are, you know, another level of hardness on difficulties. So the original paper, which looked at a two-dimensional generalization, is Barillas and Fernandez Villaverde. So they basically ran EGM with respect to one of the choices. and then they convert it back to VFI for the other choice. Their setting allowed them to not go between the two methods too much. Okay, and that sort of made it possible, really, because converting the solution may be computationally costly. Now, this paper by Ludwig and Sean, it basically looks at the problem sort of from the fundamental point of view. What is the difficulty with multidimensional EGM? And the difficulty is that you have grid like that. So if you somehow generate endogenous grid on 2 dimensions, that inevitably you have to interpolate on the irregular grid. And the standard approach is the Delaunay interpolation, right, which is costly. And you have to do it on every iteration of the backwards induction. And that's the fundamental problem that they look at this paper, and they basically, you know, show examples where doing multidimensional EGM is faster than doing simple VFI. In VFI, you control these grids, right? And therefore, interpolation on the regular grid is not is fast. So you don't have that problem at all. So that's the fundamental issue with the multidimensional EGM. Prum and Grill have a paper on computing equilibrium dynamic models with occasionally binding constraints. I think they are looking at general triangulation as well. And so it can be used in modeling. It's just more costly, right? Now we have a couple of papers. One is by Matt White, who is dealing with this irregularity of the grid in a particular way. So he says, okay, he's kind of going into the structure of these irregularities. And he says, yes, we have this nonlinear rectangle, but we can map it into something useful and interpolate the mapped, sort of the transformed functions, and then do the inverse transformation to get the values on this irregular grid. So that's a way, that's one approach to do it. Okay, transform the interpolated grid. Another approach is in Druedal and Jorgensen, which is probably the sort of the most generalization of EGM today. So they have a paper on general endogenous grid method of multidimensional models with non-convexities in constraints. So the idea there is that you break up the model or solution of the model into what they call segments. And segments basically correspond to what we had before as discrete choices. So it's like you solve for the worker, you solve for the retiree, then you compare. So in here, they have to define the segments in a little bit more complicated way, but essentially each of them produces an irregular grid. The solution is applied to each of those segments. And then you have to calculate the upper envelope of those different segments, okay? And their approach is quite simple. They say, let's recalculate on the regular grid. So just interpolate the solution from each segment on the regular grid, and then you can compare. Okay, so that's the approach. That's another approach. But what they get is pretty crazy. I mean, you probably thought that, you know, the solution to one-dimensional problem looked really unusual. Here's a two-dimensional problem. They have a problem with consumption savings and also savings into the pension fund. So these are two different savings, and I think this is optimal savings on one side, and optimal contribution to the pension fund on the other side. Right. So that's why multidimensional EGM is hard, because you have to work with these kinds of objects, and this is what consumption patient. Anyway, I think that that's another object that they have in the paper. I have 5 minutes. Okay, I'm nearly done. Now, a separate question is, can we write conditions, theoretical conditions for the class of models which can be solved by EGM? Because I hope you all sort of got the idea that if your model fits EGM, you should use EGM in some flavor. And so there's been several papers on that as well. So Matt White has the invertibility condition for the system of nonlinear equations that has to hold, right, for the model to be solvable. Again, Druedal and Jorgensen, they have sufficient conditions. And I also have a little paper where I actually focus on what the models can be solved without root finding operations, because I think that's a really a real benefit of using EGM. And so sort of a short preview of those conditions. The main thing is you have to have all the same kind of concavity, sufficient statistics. That's what we had before. That's the structure of the intertemporal budget constraint. The state variables have to be analytically computable from post-decision states. So that's the invertibility of the within period budget constraint. But the main one is this one. The Hessian of the utility function can be converted to the lower triangular. The idea is very simple, right? So if you can apply EGM to separate choices one by one, then you have to be able to recover, to invert this multidimensional Euler equation. And it's very obvious how to do if you have the triangular structure on the Hessian. But this is kind of a simple example. So I guess the takeaway here is that it's nice method, but only fits certain models. And if you have a combination of discrete continuous choices, or maybe you have, two continuous choices, one discrete or something like that, you always should try to see whether there is a generalization that applies to your case. Or maybe think of a new one, because this space is not really mapped. There is no clear understanding that, these models can be solved and these models cannot be solved. Right now, very fast about what to do with the EGM method for us as econometricians. Well, the main selling point is it's fast, right? So essentially, you can solve the consumption savings and consumption savings plus some discrete choice very many times. You can do structural estimation. You can put this solver inside of the NFXP estimator and do normal structural estimation. You can put it into some other outer loop. So this would be very useful if you have an IO application, that fits to calculate equilibria or best response functions. Just being able to solve this structure very fast, very many times for many people. For example, you can account for individual heterogeneity. Maybe you have a state variable which covers, I don't know, 1,000 or maybe 10,000 different values. But if you can solve the problem in a fraction in the thousandths of a second, right, you can just solve your model for every individual in your data in principle. Right. So that's I guess the main takeaway. It works fast, and this early paper by Thomas compares the estimation based on EGM to MPAC estimation, and you can see here that for the models that fit this this specification, there's no competition really. EGM just blows everybody away. All right, let me conclude. EGM and DCEGM is fast and accurate. That's what you have to remember. It's a good tool to have in your tool case. It applies to specific models, but if your model has, features that can be addressed by these methods, you should definitely consider that. And in the same time, deterministic discrete continuous models are intrinsically hard. I hope you remember this kinks in the value functions and discontinuities in the policy functions, and remember that these are features of the model. So you have to keep that in the back of your head when you're writing a model with discrete continuous combinations. Or you should show, how this is taken care of. And of course, extreme value shocks help. They make things more workable. Okay, let me stop here. Yep. John.
Could you tell us how long does it take your paper with Michael Keane? How long does it take?
Well, that's a provocative question. Oh, you mean like from the start of the paper to publishing? Or
No.
So the paper with Mike was estimated on my laptop. And I guess the evaluation of the likelihood function is within a couple of seconds. That's what I remember. So it's very, very workable. We didn't have to, we didn't have to go to a fancy big computer. Well, as Mike mentioned, that model is not that complicated. I'm sure many of you work with more complicated, more extensive models. So that we try to keep that model kind of small and workable. But yeah, we were working on DCEGM at the same time as we were working on the data with Mike. So altogether, it took a long time.
One of the papers that Michael mentioned this morning is the one by Blundell, Constance and Short on the female labor supply decision. And there, in the appendix, they write they tried to apply the DCEGM approach and failed. So maybe is there any actionable information from this failure as well? Were they in contact with you, and is there something particular about their setting that doesn't really?
So we had very interesting conversations and enjoyable conversations with them. Yeah, they're definitely aware of this, as you're saying, and yeah, I don't really know why they didn't go through until to the end with DCEGM approach. The specification that we're using with Mike in terms of the code implementation is not in the shape that it should be in. It was sort of a development of the code, and so maybe that's one of the reasons. We need a good software package to make it really accessible.
And there's one last question from online. So coming back to the concavity condition earlier, so how does EGM work with models of dynamic games or strategic interactions?
Right. So I haven't seen anybody use EGM in those domains, but I conjecture that if the optimization problem of the player fits the specification that EGM can work with, it's going to have wonderful implications for the tractability of that particular model as a game. It should, if the dynamic problem of the player fits into this specification, then we can calculate their best responses, and from there you're almost done. Yeah, there's one more.
I'm trying to understand how bad the snowball effect gets.
How bad which
The
effect?
snowball effect gets. So thinking of your paper with Mike, you had 6 levels of labor supply.
Right.
And a long time horizon.
Yes.
So count that.
So we have a general approach to solve any kinds of problems like that. So, I mean, how long it takes in terms of computational time, of course, depends on the dimensionality of the model and the number of decisions. But it was workable. It was absolutely okay with 6 discrete choices. And we had no absorbing in that model neither, right? So people could go between the non-working back to work completely freely.
All right.
All right.
Thank you very
No more
much.
questions? Thank you.
Thank you. Bye-bye.